Alright, today we're going to be talking about Cantor's diagonalization argument. In order to talk about this argument, we have to go over some key concepts. The first which we'll talk about is one-to-one correspondence. So, given two sets A and B, given at the top right, A being 1 and 2 and B being 3 and 4, a one-to-one correspondence is simply a function that maps elements in A to elements in B, but it has to be one-to-one and onto. So, a function that satisfies this would be something like x plus 2. And as you can see, from x plus 2, 1 would map to 3, and 2 would map to 4. Now, this is certainly one-to-one and onto, and since we can do that, we can take the inverse of the function. Well, actually, we want y, and we can map from elements in the codomain back to the domain. So simply putting in for 3, we would have 3 minus 2, which would map back to 1, and 4 minus 2, which would map back to 2, and then we would say that there's a one-to-one correspondence between the sets A and B from the 1. Alright, now let's define what determines whether a set is countable or not. A set is considered countable if it is finite, such as the set 1, 2, 3, which is certainly finite because, as you can see, there's only 3 elements, and the cardinality of this would then be 3 as well. Or a set is countable if it shares a one-to-one correspondence with the set of positive integers, which we denote the set as Z with the superset plus 1. The cardinality of the set of positive integers is denoted by the symbol for aleph null. Alright, so in our definition for whether a set is countable or not, we just said that if a set can be in a one-to-one correspondence with the set of all positive integers, then it's countable. So that is essentially saying that the set of positive integers is in itself countable. Because I can create a function, f of x equal to x, and let's say that my domain is the set of positive integers, and my codomain is the set of positive integers. Then I can easily map every element from a set of positive integers to itself in the codomain, and I can then take the inverse of the function, which doesn't change anything, and then map back. So then I've just shown that the set of positive integers is countable. Okay, so we've just shown that the set of positive integers is countable, and remember back we said that the cardinality of the positive integers is represented by this symbol, aleph null, and so it might surprise you that we can even declare an infinite set to be countable, because after all, infinite is a word we use to describe something that doesn't end. And it might surprise you even further that there's actually many sizes to infinite sets. Particularly today we'll be talking about how the cardinality of the real domain is greater than the cardinality of the set of positive integers. To prove this, we'll use Cantor's diagonalization argument. Alright, so for this proof, we'll assume that the set of reals is countable. In other words, we're going to attempt to do a proof by contradiction, because before we had said the set of reals is uncountable. Because we're assuming that the set of real numbers is countable, let's isolate a smaller set. So the set from 0 to 1 of real numbers is certainly a subset of the entire real domain. So if the set of reals is countable, then certainly the set from 0 to 1 is also countable. And so next what we're trying to do is we're just going to try and take the set from 0 to 1 and create a bijection to the set of positive integers. Or in other words, we're going to try and create a one-to-one correspondence between this set and the set of positive integers, and that would allow us to conclude that the set from 0 to 1 is countable. Alright, so let's represent the set from 0 to 1 of reals as this table. And notice we've got R1, R2, R3. Let R1 through Rn be the numbers in 0 and 1, 0 through 1, and each digit will be d sub I sub j, where I is going to be the row and j is going to be the column. So for instance, d11 would be the first row and the first column. And so dij is going to be an element of this set, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Alright, now we're going to declare a new number a. We're going to define it similarly to the r's above, such that 0 point a sub 1, a sub 2, a sub 3, a sub 4, and so on correspond to the digits. So the rules we're going to say here is that a sub I cannot equal d sub I. So if we look at that graphically, a sub 1 here has to be different than d sub 1, 1. Similarly, a sub 2 has to be different than d sub 2, 2, and so on. As you can see, we're making a diagonal line here through all of the d's. What this means is that the number a is always going to be different from any of the numbers r previously defined. Because we defined all of the set of all the r's as all of the numbers between 0 and 1, but we just found a new number a that must be in that set, there's a contradiction. Even if we added a into the set of r's as some r sub n, we could create a new number a because there's a new diagonal that's created when we put in our old a. We know now that the set of r's must be uncountable. And you might be thinking, what if we started off with a included in our set of r's? It would still be shown as uncountable, because even if we had that a as some r sub n, then we would have a new diagonal which would yield a different a. Alright, we've just shown that the set of numbers between 0 and 1 is uncountable, and we know that that's a subset of all real numbers. Consequently, we must know now that the set of all real numbers is also uncountable. Alright, previously we told you that the cardinality of the set of positive integers was Aleph null. But now we know that all real numbers is uncountable, whereas the set of positive integers is countable, which means the cardinality of real numbers must be greater than Aleph null. You might be thinking, how is this possible? Aleph null is already an infinite number. Well, we know that the cardinality of all real numbers, now being greater than that, has to be some degree of infinity larger than Aleph null. And in fact, Aleph null is the lowest degree of infinity.